Okay, good. Today we are going to start with our second physics module, which is the thermodynamics and statistical mechanics. With this module, we are going to do or to have two parts: thermodynamics and the other part, which is statistical mechanics. So, with this thermodynamics, what you have to actually do in order to can get higher grades or the grades that you desire, you have to actually go through this text. You have to actually read, read the whole text. And after reading, or while you are in the process of reading, you must take note of the basic terms. There's this term which is macroscopic. You have to understand what is the meaning of macroscopic. You have to understand the meaning of the word macroscopic. So when we say something is macroscopic, we're actually talking about systems. So when we say a system is macroscopic, we are referring to when we say we have a macroscopic system. You say system, or you just say macroscopic. So saying a system is macroscopic, we are saying that the system is a system that contains a large number of particles. It's a system that contains a large number of particles. You can think of an example, e.g., a classroom. A classroom. Taking note that in that classroom there are students, right? So we consider those students as particles. And we also have to talk of what you call microscopic. This one, just microscopic. Microscopic. When we say we are dealing with microscopic system, okay, it's also a system. Now, when we talk of this microscopic, we are going to talk of properties, the properties of each particle in the system, in a macroscopic system. So when we actually talk of this microscopic, we are referring to the properties of each particle. So it means we are going to talk of the properties of each student in that classroom as an example. So it means we're going to check the properties of each student. It can be the marks of the student, the marks of each student, of each student, the marks of each student, and what else? The date of birth, and so on and so forth. You can think of any property for your example. It's up to you which example you can talk of here. I said my example for macroscopic system is a classroom. So when we talk of microscopic system, we are going to talk of the properties of each particle in that macroscopic system. I hope this makes a good sense. Now, let's talk of what you call the scope of TD, which is the thermodynamic scope. The thermodynamic scope. What are we actually talking about here? When we talk of the thermodynamic scope, we are referring to the focus that thermodynamic is actually having, or we are actually focusing, or it's what we are actually focusing on this thermodynamics. What are we actually focusing on with this thermodynamics? So the scope of TD is just referring to the importance that we are actually looking for in this thermodynamics. So we're going to talk of the physical properties of the macroscopic system. Physical properties, physical properties of macroscopic systems. And another one is the relationship, is to identify the relationship between it and other properties. So we know about this heat, right? So we have to identify the relationship between that heat and other properties like pressure, yeah, and other properties like pressure, or you can just write P. You can just write P for pressure, like pressure, density, temperature, volume, mass, and so on and so forth. You can think of any type of property that can be related to heat. So we're going to check the relationship between heat and pressure, heat and density, heat and temperature, and so on and so forth. That's the scope of this thermodynamics. And now we talked of macroscopic systems and also microscopic system. Now, what are we talking about when we talk of a system? What is a system? What is a system? A system can just be defined as a position of the universe enclosed by a real or imaginary boundary. This system is a position of the universe. So you can think of any position in this universe. It can be in the sky or anywhere, as long as it's in the universe. That position must also be enclosed by a real boundary or an imaginary boundary. So an imaginary boundary and real boundary, how can we identify that? So let's let's have this as an example of a system. We have this as an example. We have this as an example, and you can see that we have a boundary here. There's a boundary in this system, and this one is our surrounding. It's our surrounding. It's our surrounding. It's our surrounding. Then this one is our system. Then this one is our boundary. And you can see that it's a real boundary. System, surrounding, and there's a boundary. And then now, when you talk of an imaginary boundary, inside this boundary or inside this system, you can think of having another boundary. So that one will be regarded as an imaginary. Regarded as imaginary boundary. Imaginary boundary. Okay. So that's it about the imaginary and real boundary. So this one is real. This one is a real boundary. It's a real boundary. Okay. So under these systems, we also have the three types of systems. We also have three types of systems. We have three types of systems. The first one First one will be an open system. An open system. What is an open system? An open system is a where system where energy and matter or mass. You can say the energy and matter can be exchanged with the surrounding. With the surrounding. System where the energy and the matter can be exchanged with the surrounding. Both energy and matter, both energy and matter can be exchanged with the surrounding. That is what we call an open system. That is what we call an open system. We also have what we call a closed system. A closed system. What is a closed system? This is a system where energy, this energy you can regard it as a heat. So it's you call it energy or heat. Energy is heat, but not matter. Is exchanged with the surrounding. That's a closed system. That's what we call a closed system. Only energy is exchanged with the surrounding. Then we also have what we call an isolated system. An isolated system. An isolated system is a system where neither energy, which is heat, nor matter, which is mass, is exchanged with the surrounding. With the surrounding. Neither energy nor matter is exchanged with the surrounding. That is an isolated system. Then now I want to give the examples or real life examples for what, for this system. real life examples. We have for an open system. For an open system is going to be a cup of tea, a cup of tea. You know that cup of tea will just be something that looks like this. There will be some steam evaporating and also heat that is being transferred. So because of that, we will have what we call an open system. The steam is going or is evaporating some mess. So that's why we are regarding it as the exchange of matter. And then we also have an example of an isolated system. An example of isolated system. I mean, of a closed system. Before we can go to isolated, let's talk of a closed system. An example of a closed system is going to be that same cup, that same cup, that same cup of tea. But now we make sure that we close the lid. Make sure that no matter is exchanged. Yeah. Now we have closed with a lid. So only heat is transferred. Only heat is transferred. Then an example of an isolated system we said is a flask. A flask. A flask. You know that a flask is going to be something that will never, there won't be any heat loss. There won't be any heat loss, right? So we call it an isolated system. We call it an isolated system. And also matter is not lost because we are closed the lid here. So matter and heat is not transferred. Matter and heat is not transferred. Someone might ask about what if we were talking of the real flask, because a real flask, if you put it probably after one day, it will be cold. The water will be cold. So yeah, it's not actually an ideal flask that we have, but the ideal flask that we wanted to have should have retained the temperature or should have retained the heat. So there's a difference between real and ideal. So the one that we wanted is ideal, which it's supposed to retain the temperature. But then the real one is what we are having now. So we just assume that this flask is an isolated system. It's an isolated system. Okay, good. So we are going to now talk of what you call state variables. State variables. What are state variables? These are measurable quantities, measurable quantities that specify this, the state of a system. Simple to define this. State variables. You see, it's self-defined. It will determine or specify the state of a system. And another important term, we have what we call extensive properties. Extensive properties. What are extensive properties? These are properties or quantities. To say, yeah, let's call them quantities. Quantities that are proportional to the mass of the system. Quantities that are proportional to the mass of the system. What are we actually referring to? We can think of us having we have a system like this. We have a system there, and we can see that, let's say, for instance, there is a gas inside. We have a gas inside that system, and again, we take because the system you can see it's now the volume is in this way. We have volume which is V, the volume of that system. We want to check whether volume is proportional to the mass. So now we are going to divide this into, we'll divide the volume in two. So we'll have one and then another one, which is, so what happens to the volume? We can see that the mass is no longer, the mass is no longer the same. The mass is no longer the same, but what about the volume? Also the volume, you can see that has changed. It's V over 2 now instead of V. So it means volume volume is an extensive property. Volume is an extensive property. Now you can also check another property, which is, let's say, temperature. Now let's check temperature. we have this. We have that block temperature here. You can see. Let's say there are some particles or gas there. So we measure the temperature. We got a certain temperature. Then now we divide that block into it's going to be something like this. Then what happens? What happens to the temperature? What will happen if we measure the temperature here? It will still be T. Even here it's going to be T, meaning temperature is not an extensive property, but an intensive property. So now you know also what we call an intensive property. Temperature is an intensive property. So when we talk of an intensive property, we're talking about properties that are not proportional to the mass. Properties that do not depend on the mass. Let's talk of another property, which is heat. Heat. Okay. Let's talk of the heat. When we talk about the heat now, we are talking about a different property. Okay, let's talk about heat now. If we break them into two, Q here and Q here is also going to be probably divided by 2. It's going to be Q over 2. So heat is an extensive property as well. It depends on the mass. It depends on the mass. Extensive property. It is an extensive property. Okay. Now let's move to our. Let's go back to our document here. So after you have read page 1, you must know what are macroscopic systems, microscopic properties. Okay, you see, we talk of properties when you talk of microscope, but in any ways you understand when you talk of macroscopic and microscopic. So also you must know the scope of thermodynamics. So now I was talking of what you call state variable. State variable. So here in this unit 2, you can see we're talking of the state of the thermodynamic system specified by the values of a certain experimental measurable quantities called state variable. So yeah, you have to go through the text. Every information is there. And then We also have energy, work, heat of a system. You know what thermal equilibrium is, or you have to know what thermal equilibrium is. Yeah. Uh, we talk of what we call thermal equilibrium. Thermal equilibrium. Thermal equilibrium. What is the meaning of this thermal equilibrium? Suppose we have two objects, A and another one, which is B, and they are in thermal contact. You can see that we place them into close or close to one another. So if A was having a certain temperature, after some time, both of A and B will reach a certain temperature. They will reach a certain temperature. They will reach a certain temperature. So that's what we call thermal equilibrium. So it's when the exchange of heat between A and B has come to an end. So we are now having A and B no longer changing the temperature. They are in thermal equilibrium. They are no longer exchanging temperatures. They are in thermal equilibrium with one another. That's what we call thermal equilibrium. You also have to understand what's the meaning of the term. Okay, here. Okay. Yeah. We also have to check these questions, and I'm probably sure, but I'm actually sure that next on our session we're going to deal with these questions. So we have to go through all these questions because they are the reason why some of us made it. They are the reason why we managed to pass this model. Everything is there, just that you might not know how to use it. So let's meet again on our next session. Have a good day.